Hello everyone, my name is Professor Polish, and in this section I'll be giving you an overview on CMP polishing pads. I will tell you a little bit more about their composition, how they are made at Cabot Microelectronics, and their importance in the CMP process. Pads are the next big part of CMP. They are usually made of a hard polyurethane foam, are cut into discs, and laminated onto a subpad. Pads have circular or crisscross grooves on the surface. Sometimes pads come with windows that allow sensors to monitor the polishing process. The pads attach face up to the rotating platen on the CMP tool and spin at around 100 RPM. Slurry is poured onto the rotating pad surface. The spinning wafer is pressed down onto the pad that has been saturated with slurry. The pad causes the rolling, sliding, and bouncing of the nanoparticles that slowly wears away the wafer surface. Chemicals fine-tune the process. Pads are quite expensive, often several $100s each, so customers want them to last a long time, hundreds or even thousands of wafer passes lasting hours or even days before they need to be replaced. Why don't they last forever? To understand this better, we need to look in more detail at their structure and how they are made and used. Pads generally come with grooves and pores, as you can see in these micrographs. Our understanding of pad mechanics is not complete, but we do know that grooves are important, mostly for transporting slurry into the process and polishing byproducts away from the process. Pores also play a critical role in holding slurry close to the wafer. We deliberately pop the bubbles on the surface of the pad using a disc of sharp diamonds called a conditioner. When the pores are scored with the diamond conditioner disc, a number of them pop open, and the tongue-like flaps that form are called asperities. These stick out from the surface of the pad and are what makes direct contact with the wafer during the polishing process. Usually only about 0.1% of the area of the pad actually touches the wafer. You can see why the size and shape and hardness of the pores are so important, because this is where the rubber meets the road. After polishing for a while, the asperities soften, maybe melt, get caked with debris, lose their resiliency, and need to be replaced. The diamond conditioner continuously or intermittently shears away the pad surface and creates new, fresh asperities. This drawing was adopted from Len Baruchi's work at Arica, showing how different asperities might contact the wafer. The picture below is from Abhi Prasad, showing what the asperities look like under high magnification. As I mentioned, the asperities are really what contact the wafer. They represent about 0.1% of the total wafer area. So if a process runs at, say, 2 or 4 or 6 pounds per square inch, that might not seem like much. But if only 0.1% of the pad is making contact, this is really a force of 600 pounds per square inch. Imagine one 300-pound sumo wrestler lifting a second sumo wrestler over his head and standing on one toe. That's heavy. No wonder we get some scratches from time to time. In CMC's process for making D200 pads, we can control the size and concentration and hardness of the pores. Here we see what 15, 20, and 40% porosity looks like in the foam. As I mentioned on the last slide, we can also independently control the pore size, in this ranging from 2 microns to 130 microns. To put these sizes in perspective, a 130 micron pore is 1,000 times bigger than a 130 nanometer feature on a chip. So you can think of these asperities as huge tongues of rubber sliding along the wafer surface. Since particles are also around 100 nanometers or less, you can envision hundreds or thousands of particles absorbed onto a single pad asperity. It is probably unlikely that the bare rubber contacts the wafer surface. More likely there are particles and fluid riding and rolling in the gap. CMC has 2 unique approaches to make pads. In the D100 process, we dissolve the rubber resin into carbon dioxide at high temperature and pressure, at a point where the CO2 is supercritical. Not quite a gas, but not quite a liquid either. Then we extrude the supercritical mass through rollers, and as the sheet enters the atmosphere, it cools, quenches, and depressurizes. The rubber hardens and the CO2 turns into a gas at the same time, leaving it very uniformly porous on the inside. The second process that we employ for D200 is to take a roll of crystal clear rubber already extruded to about the right thickness. We then place the roll in a chamber containing carbon dioxide and pressurize it for several hours to saturate the rubber with CO2. The molecules in rubber are long and flexible enough to take up a lot of CO2. Then we quickly drop the pressure and flash heat the entire roll, and the dissolved CO2 causes the rubber to suddenly foam like popcorn does in a microwave. By controlling the pressures and temperatures and times, we can fine-tune the pore size and concentration. Pretty clever. Another big difference between Cabot Microelectronics rubber and the rest, we use something called thermoplastic rubber, and all the other guys use thermoset rubber. In thermoplastic, the rubber is made up of long polymer molecules that basically tangle up, and this is reversible. If you heat it, it flows, and if you cool it, it is stable. With thermosets, however, they cure the rubber permanently using chemical bonds. Once you've cured a thermoset, it is permanent. Can anyone guess why this difference can be important? Here are a couple reasons. During the polishing process, the interface between the wafer and the pad heats up, sometimes a lot, from room temperature all the way up to 60, 70, or 80 degrees centigrade. Our thermoplastic softens, which can be great for reducing scratches, but it also makes our rubber more difficult to condition. We can also tune the hardness or modulus of the rubber. In general, the harder the rubber, the more likely we are to see scratch defects. But hardness also improves the removal rate and uniformity, so we have to make trade-offs to optimize the process. For buffing processes where extremely good final surfaces and low scratch are critical, but removal rate is not too high, then the soft 42 durometer rubber works well. For higher removal rates, for example during the first step bulk removal of copper or oxide, a harder pad is usually best. So, where are we in our learning? We understand how CMP fits into the semiconductor manufacturing process, and that it uses a tool, a wafer, a slurry, and a pad. We learned in the previous section the different components in slurry, and now we learn that pads are also complex, with pores and asperities that control the mechanics of polishing. We learned that our process uniquely allows us to tune the hardness, the porosity, and the pore size, and that Cabot Microelectronics uses a thermoplastic, unlike the rest of the pad designers. Now, let's look at some of the things that can go wrong with polishing.